Hello, everyone. Good evening to everyone who is joining us from India. Good afternoon to all our Middle Eastern, European, and African folks who have joined us. And good morning to everyone who is joining us from the West. I'm Moin Matar Naik and I'm representing Seed Global Education today. We are a higher education firm based out in the United Kingdom, and we help high potential students in making their dreams of either studying an MBA, a STEM master's, or a business master's in top global universities a dream reality. We are live right now, and I can see many of y'all have started dialing in. Many of y'all have joined us on the streaming on YouTube. For all those who have dialed in on this call, if you can let me know in the chat as to which city are you dialing in from exactly. Which city are you guys dialing in from? If you can put that up on the chat as to which city are you guys dialing in from. We have students who are joining in from Kashmir, India, from Ahmedabad, Gujarat, students from Durgapur, Kolkata, Durgapur, Bhubaneswar. We have many students who are joining in from Warangal, Mumbai, Pune, Hyderabad, Bangalore, across the lengths and breadths of the entire country, students are joining in from. All right. Today, for the next 60 minutes, we are going to be talking on an exclusive topic on the atomistic simulation and modeling of high performance engineering materials. Today, we would be learning more about understanding the fundamental principles of RMD simulations, insights into optimizing materials for high impact, high stress environments, understanding the role of nanoscale engineering in improving energy release and efficiency, and exploring how atomistic simulations can drive innovation. This session today is brought to you by Loyola Marymount University Seaver School of Engineering. The Frank R. Seaver college graduate programs at LMU are designed with students in mind. Their curriculum supports the need for advanced technical knowledge, enhanced professional growth, and deepened understanding within the chosen industry. They have a wide range of graduate programs in environmental sciences, civil engineering, mechanical engineering, electrical engineering, and computer engineering. But before we go any further, I have a quick poll for all the students who have joined us. And I would be going live with the poll in a minute. Here is the poll on your screens. What are you hoping to gain from this particular masterclass? Are you looking forward to understanding the principles of RMD simulations? Are you interested in learning about applications in high performance materials, exploring the role of nanoscale engineering, or gaining insights into research opportunities and more information about university programs? What exactly are you guys looking forward to from learning from this masterclass? We would be waiting for the next 10 seconds for everyone to drop in your answers. Last 5 seconds. All right. So here are the answers which have come in. Many of the students want to know more about the role of nanoscale engineering, where many of the students are looking forward to gaining more information about the university programs. With this, moving forward, introducing the panel members who have joined us today, we have Dr. Hong, who is the Assistant Professor of Mechanical Engineering at Loyola Marymount University's Frank R. Seaver College of Science and Engineering. Dr. Hong's goal is to provide students with tangible experiences in computational modeling, virtual reality, augmented reality, and to motivate to learn cutting edge skills and pursue careers in science, technology, engineering, and mathematical fields. Dr. Hong's career, research career spans a wide range of scientific areas, particularly focusing on the use of computer modeling simulations for chemical and material processes. His work has garnered significant recognition, securing approximately $1.2 million in funding from various sources, including state level programs, federal agencies, and global industry academic collaboration. Thank you so much for joining in with us, Dr. Hong. Also, we have with us Miss Emily Agnello, who is the Assistant Director of Graduate Recruitment at Loyola Marymount University. With over 7 years of admission experience, Emily has passion about working with students to help them take the next step in their career through enhancing their education. Thank you so much, Emily, for joining us today. With this, I now hand over the floor to Dr. Hong for the next set of the session.
All right, thank you, Moin, for your introduction. So now, is it my time? Can I share my screen? All right, all right. So I'm going to share my slide. This is my okay. All right. Hello, everyone. Hello, good morning or good evening in India. So I think I have more than is about 190 student, which is amazing. So thank you for joining this event. So again, my name is Leo Hong, and I'm Assistant Professor of Mechanical Engineering at Loyola Marymount University. This is my topic. So, atomistic simulations and modeling of high performance of engineering materials for student success in STEM field. So, in other words, I'm actually working on computational modeling for my research, and I'm also collaborating with my research topic with all education people, like how to better teach physical chemistry in classroom. So that's overall goal of my research. Okay. So I'm going to introduce my research topic and my recent effort and my future plan during this presentation. Okay. Yeah, let me go ahead. Let me briefly introduce myself. This is my research lab website. Maybe I can share this one in later. Okay. So this is my research lab. So I just started my career at LMU last year. So this is my new lab at LMU. So the name Atomistic Simulations Pioneering Intelligence Research and Enhanced Virtual Reality. I'm using my molecular dynamics. I'm using my virtual reality, VR, augmented reality, AR, and some machine learning and AI to better design engineering material. Okay, so this is my website, and right, this is me. Just because I just started my research career at LMU here last year, so I have two students, one graduate student, the other one senior student, Hugo Tavares and Joaquin Cabanes. Okay. So let me just briefly tell you overview of my research at a glance. Okay, let me use my laser pointer. So my research is based on atomistic modeling and simulation, specifically molecular reactive molecular dynamics. So using this skill, I'm doing computational design and discovery of engineering materials with high performance, and we can just measure, investigate properties of material and their application to many engineering fields. And using this topic, my main outcome was like published paper in very high impact journal like ACS Nano Letters, and some like Nature Communications, like the very high impactful paper. And then I'm a big fan of student involvement in research. This is kind of hands-on, like doing simulation on their PC or laptop, so they can model and design their simulation on their personal PC or MacBook, any personal desktop. Okay, and then as like I mentioned, I'm also working with education faculty, like to better teach STEM field. So basically, I need interdisciplinary team effort, and then using STEM pedagogies and some culturally relevant teachings for to promote better like diverse atmosphere, and then better teach science and engineering mathematics field. So based on this topic, I got many federally funded grant from NSF and USDA previously. Okay, this is my major outcome during using this STEM education field. And by combining my molecular dynamics and STEM education, my overall goal is to let my student do real world engineering problem solving. So like not just limited to their like theoretical part, also apply their knowledge to like industry related problem, like how to tackle the problem faced in industry or company. So I'm active collaborator working with local industry like aerospace companies or some other research lab. So, so one of the example was I have been working with Samsung like to better design glass model, glass ceramic model. I will discuss this one in later slide. Anyway, this is like overall goal to promote inclusive and equity and diversity in STEM field. Okay, and this is like overview of my research. And then I'm going to go over my major main topics today. First, introduction to MD, molecular dynamic simulation, which is very popular in computational field. And then let's go over this one first. Here's the overview. I'm talking about atomistic scale simulation. So this plot shows the scale, smaller scale to larger scale. So we are lying in this green part, force field method or quantum mechanics method. So basically, my research is based on this force field method. So here, green part is about taking care of about the scale in nanoscale using simulation. So basically, using this force field method, we can describe um, materials behavior at the atomic level for up to very higher number of atoms and very high temperature, up to numbers atoms like 1 million or 10 million atoms, but we need very high performance, high-end computing, research computing to make this possible. Okay, next one. So I'm gonna I'm gonna skip the very details about this method. So anyway, we are working on Newton's second law, force equal mass times A, d squared r over dt squared. So using this formula, we can just apply force field. Again, the force field is the force describing interaction between atoms. For example, if I have carbon or if I have oxygen in my system, I need force field for carbon and oxygen interaction. Once we get it, you can just numerically integrate this Newton's second law twice, that you can get velocity and you can get velocity and positions of the atom as a function of time. In other words, we can just track the positions and velocity of atoms during our MD simulation. So once we get reasonable force field, we can describe like MD simulation as you can see on the right video here. This is like tensile stress simulation. Stretching the sample, but crystalline here, all the carbon, bond breaking happens along these blue boundaries. So this is what we can do during MD. We can just do mechanical simulation. And next, I'm going to introduce some not basic, applications of MD simulation to engineering field, like aerospace field and some mechanical engineering or some other field. So I'm going to introduce few videos using our MD simulation. First, aerospace application. Okay. This is one example. This is space shuttle. When this space shuttle is running, shoot it into the sky, there is a like many debris or meteorite, dust, grain in the air. Maybe that small particle, even very small particle with hitting the surface of this external tank here. Even that is very small because this is very fast shooting up. It will create the very severe damage on the surface. May possibly potentially make some disaster. So this is one problem in aerospace field. If we want to do experiment for this one, this is extremely expensive, extremely dangerous. However, we are using computer simulation to simulate this kind of damage impact on the surface to learn how to better design materials like shape or dimensions or materials type. So next one, this one is showing the simulation, just reproducing this damage situation. For example, this blue one is the surface of the tank, external tank that I showed in the previous slide. The gray one bullet shows the like debris or grains or the dust in the air hitting the surface. So when playing this movie, you will see how damage initiated and how damage propagated and finally what happened at the end. This is fully atomistic. Everything is all atom. You see the color variation is showing the pressure of the each single individual atom propagating the color, and then you see the cracks hitting the surface, and all this is fully atomistic, reactive molecular dynamics. Okay. All right. So this is one example applying our MD simulation to engineering field, how to better understand fracture mechanics and how to better understand how to design the high performance materials. Okay. Next one is another example in aerospace field. This is like silicon carbide, SiC, which is very popular material for external shield material for aircraft in for aerospace field. But as you know, when this aerospace runs in the space, this material undergoes very high temperature or high pressure situation. So we want to know the oxidation of this silicon carbide material to see how to control its chemistry. So here in the black background, oxygen is missing. It's just for better visualization. In the next video, you can just assume that there's oxygen in the surrounding, just like air. And this one center is silicon carbide nanoparticle. And then I'm playing the movie, fully reacting each other when oxygen is hitting the surface. And it's like you see the structural evolution. Silicon carbide turned into different material, different types of shape or different types of material composition, chemical composition. So at the end, you see the full evolution of structure. Finally, it forms like carbon sheet, which is graphene, and also another silica cage like SiO2, and the surrounding you see CO2 gas. Everything is like fully dynamic, fully reactive. So anyway, MD simulation can do fully reactive simulation to understand the chemical reactions during like engineering processes. Okay. Next one is just like kind of mechanical. If you are in mechanical engineering major, you may do some tensile stress testing. Bring the sample and stretch the sample up and down. Then you will see the crack depending on the strength of the material, like metals or glass, whatever it is. Then this is one example reproducing that realistic tensile stress simulation. So as you can see here, this is glass. Glass, you're using your phone. The glass screen, touch screen, that's all glass ceramic. So this is glass made of like sand, SiO, and this is the sand model, glass model. You're stretching the sample up and down. Then let's see what will happen. You see the crack initiation happens along here and propagation along this y-axis, and it's like the sample is broken like glass, like brittle material. If you throw the glass in the ground, you see the materials are broken like brittle material. This is because glass is one example of having brittle property in mechanical engineering. So this is what you can see using MD simulation. Also, we are looking at atomistic view. How this happened, why this happened during this fracture. So as you can see this right panel. So one bond here, silicon yellow, oxygen red here. One is will be broken and then during this fracture, and then the other bond will be formed in neighboring silicon transferred to neighboring oxygen here. Then you will see the fraction mechanism. You see one broken and then it goes to the neighboring forming during this fraction process. So this is what you can see using MD. Again, this can be possible using MD because we are simulating atomistic behavior. But even you're using very expensive, very high-end experimental device, you cannot observe this one. Or you never see this one using your naked eye because this is very, very small scale. Even 0.1, 0.1 nanometer, we cannot observe this one using our naked eye or even very high-end experimental devices. But we can see this one using MD, atomic scale simulation. Okay. Another example, nanobubbles collapse in the silica surface. Okay, so we are looking at this yellow slab. So just any slab you can just see in your daily life. And then there's water on the blue part. Inside the water, there's a bubble, spear shape. And then you're providing shock to the water bubble. And then let's see how water bubble transformed into the different shape and then hitting the surface. Here, water, you're looking at the inside of the water. This is like nano bubble, like spear shape, and then just a shock is coming from to the right. The the blue representing the shock hitting the blue spear, then bubbles is like shrinked and then transformed into like nano jet hitting the surface of this yellow panel, creating some damage on the surface, showing this one. You can see here is a dent on the surface. Okay. We can also do very details about this damage mechanism using like detailed analysis during MD trajectory. Okay, this is another example. We can see uh, the fractures or damage patterns on the surface of engineering material. These are the very good example we can use. We can apply MD simulation to engineering field or science field. Okay, another example like materials fracture similar to the glass. We can see how materials are broken up by applying the right and left like tensile tensions. So see the crack propagation along this direction. And then this is a good example to better understand this crack mechanism or crack patterns in engineering materials surface. And one more, the right panel, there's something like this is one example we can collaborate with like um, lead companies in like smartphone devices or screen, TV or monitor using very requiring like very high strength glass material. For for example iPad, there's a screen. People are not no longer using finger to draw to write down something. They're using Apple Pencil to hitting the surface. Then if that hitting the surface happens multiple times, finally the material of the surface of the glass will be broken. So this is one example, yellow representing some Apple Pencil, the gray representing surface of like your tablet PC. You're hitting depending on the shape of each tip of the Apple Pencil. Let's see, designing different shape dimensions. We can just understand like this one is top view, showing the like damage propagation on the surface of glass alumina surface, showing that you can understand this damage propagation, its pattern. And by applying different types of shape or dimensions of the Apple Pencil, we can just better understand how to better design to minimize this damage propagation. Okay, so this is another example we can use MD to understand its mechanical properties or damage. So those are the examples of MD simulation to be applied to engineering field. So now I'd like to introduce my recent research effort, my current research topic that I'm using. This is one we can try. Okay. For example, I'm working on computational synthesis of this semiconductor devices, like 2D devices like MOS2. This is very popular in engineering field right now. So like which can replace the graphene, having very promising electrical properties. So this is like one example how to model these semiconductor devices using um, reactant like MOO3 and sulfur on the top. By reacting each other, we can just simulate how this happened and why this happened. Okay, then next one. Uh, so here's an example. First, here's the challenge. Experimentally, the synthesize the material MOS2 using sulfur gas and MOO3 that I showed in the previous slide. But when they are working on that synthesis, it is kind of fully reacting each other, leading to MOS2. However, the initial MOS2 is not that crystallized. crystallized means that the atoms arrangement is not well organized, but it's just like amorphous, like fully disorganized. If the materials are disorganized, we cannot get expected property like electrical properties depends on that arrangement of the atom. But anyway, we want to get very highly ordered atom, which is crystalline. So in MOS2, there's 1T phase green, 2H phase in two different types of crystal phase. So here, first one, as you can see here, blue, fully amorphous. It's disorganized at the beginning. But we did simulation using this one, but we are wondering how to crystallize this one using different like technique. So what we suggest here is that, okay, let's do the like annealing, temperature going up and down, multiple annealing cycle to see how the materials are evolving. So as you can see here, so we are just fast means that high temperature, slower means that low temperature. You see that the blue part is transferred to green and green to red, meaning that this is like crystallized. Even though we are having some grain, but it's much better than before. At the end, you will see the very bigger portion of the the, the red one, 2H crystalline phase at the end. As you can see here, here the zoom in view, all the like crystalline phase, like you can see the like all the honeycomb like shape. So as you can see here, if we get something like this kind of crystalline phase, we can get expect higher electrical properties. That's what we want to do as an engineer. Okay, this is great support for experimental design because computational design can also support experimental design. As you can prove here, okay, let's do the annealing, then we can get crystalline phase. This is one example we can try. Okay, another example, we can just do like designing high performance of aircraft vehicle, the fuels like hydrocarbon fuels. As you can see here, this one runs really fast, very high temperature and high pressure, which is called hypersonic, very high velocity. So anyway, so we are using these fuels, hydrocarbon fuel, under this extremely high velocity and high temperature, high pressure. So we can just simulate this hydrocarbon behavior. As you can see here, this is all hydrocarbon. This is called JP10, which is very popular in aircraft industry. They're using this one as a hydrocarbon aircraft fuel. All fully reacting each other. They are moving really fast, very high temperature. This is kind of like extremely condition as we see in the previous movie. Very high velocity, very high pressure, and very high temperature. So as you can see here, they are reacting each other, forming some different types of this. You see that there's reacting each other, leading to like green, like carbon sheet, which is graphene. So anyway, this will be evolved into like soot during combustion. As you can, do you guys know soot, which is a black carbon product during your when you burn something. So as you can see everything like this kind of atomistic view, any fuels are burned, something like this one here. Okay. And one more, my recent effort is that in addition to the pure hydrocarbon uh, pyrolysis, what if we add some um, additive in the fuel, like this kind of one, functionalized graphene with a nanoparticle, because this will give you higher performance of the energy fuel. Okay, so here we are adding this kind of graphene sheet in the full, as you can see in the right panels. So see middle, and this is kind of ongoing research. So you can see all those. So we are also adding the nanoparticle in the system. Anyway, we are doing nanoparticle and graphene sheet and fuels to see the energetic performance of these kind of fuels. So our goal is to design higher efficiency of the fuel using multiple like composite. Another ongoing, we are designing glass ceramic to be applicable to aircraft windshield. As you can see in this picture, when aircraft is operated, there is some accident by like bird or some grains or other debris in the air hitting the window shield, making a crack. This is like very severe problem in engineering field. And when engineering field, we are trying to design this material using this kind of grain in the in the main glass body. As you can see in this A, you're looking at grains inserted into this glass ceramic model. So as you can see here, this will give you different mechanical behavior. Pure glass model on the top and the bottom having multiple grains. You see that cracks are different behaving as you can see in this figure A. So different types of SS graph because of that grain inserted into the glass body. Okay, so these are all the science, engineering, basic science thing that I introduced before. And I'm also working with STEM education using my research technique software, RMD. So this is my ongoing project, working with multiple collaborator with outside the LMU. So I have many collaborator working on science education, special education, and computer science, and some other food science, agriculture topics. And this is like very interdisciplinary effort to make to promote STEM education. So we are applying multiple grants. So these are the ongoing two projects by NSF and USDA. We also submitted another grant last year, yes. And then this is kind of ongoing. So this is basically we want to use our simulation and AI or machine learning to teach chemistry better. That's the overall theme. And this is like conceptual things. So as you can see here, right panel, let me just briefly talk about this topic. So so this is what you can do during your high school or elementary or middle school. You're doing chemistry using textbook 2D, like text-based one, like when talking about chemical reaction, forming the water, right-hand side, left-hand side, you have hydrogen and oxygen. This is a conventional way of learning in classroom. Maybe this is way too abstract. Sometimes students don't understand why this happened and how this happened. So we are using computer simulation with the VR. So they are wearing VR and then playing with the molecule and atoms and getting closer to the system and touching the molecule, and then they can do simulate all the reaction happening along this kind of step by step. Okay, this is one approach we are trying to better teach physical chemistry. Okay. Anyway, so this is like pilot study. So we are just like get pilot study for the student. This is very positive feedback from the student. As you can see here, they are providing very great feedback. This was really good, motivated, and we really liked it. And they improved my STEM identity from here to here. I feel like I'm STEM professional after learning this simulation technique. Okay, so we keep developing this system or this program module to better teach chemistry in future. Okay, future direction. Anyway, so let me just quickly finish this one. So anyway, this is all my overview. I'm using computer simulation and I'm using VR or AR, VR here, AR to better understand chemistry. This is my overall goal at LMU. So I'm big fan of student involved research. So I'm trying to get the research grant from like federal grant or local grant to promote undergraduate research. And also LMU has multiple opportunity for summer or research program or symposium for undergraduate student. So this is my ongoing effort. Plus, I'm also a big fan of industry academia collaborated research. I have many collaborators here in local, Air Force Lab and Northrop Grumman in one of the big aircraft company in local, and Sandia National Lab and also NASA working on like aerospace related topic. Anyway, the goal is to let my students develop their STEM identity and then pursue their STEM career after graduation. Okay, so sorry, I was a bit running fast. So this is my presentation, and thank you for your attention. And then I'm happy to take your question if you have any. Okay. Is it? All right.
All right. Thank you so much, Dr. Hong, for such a wonderful presentation on atomistic simulations and all the materials which are involved when it comes to high performance engineering. Dr. Hong, we have been getting quite a lot of questions on your presentation. Taking the first question, Prateek over here is asking us, while we are running these kind of atomistic simulations, how can we ensure that all the minuscule details, all the outliers are captured and actually translated into the material's real world performance?
Okay. Is it questions from the chat or?
Yep, it is from the Q&A section. Yep.
Okay. Let me see. Uh, Sorry, can you repeat the question again?
Yes.
So I cannot see the
So
questions on the
Prateek
box.
over here is asking us, while we are running these atomistic simulations, how can
Yeah.
you ensure all the minuscule details are captured and translated into the material's real world performance?
Right, that's great question. So basically, when doing MD, we have to validate our result with like another smaller scale, like called quantum mechanics simulation or DFT simulation, plus a macroscopic experiment. For example, let's say I got some result, which is chemical reaction. So once you get the chemical composition, so we compare this one with realistic experiment. When they experimentally do some their experiment, they will see some chemical composition measuring something using their high-end device. Then we compare their result and our result. This is first validation to ensure this is okay, this is reasonable when comparing to realistic scale, and also more smaller scale like quantum mechanics. Okay, still feasible, still makes sense. Then we can say, okay, our model is valid and okay to use and you okay to present.
All right. Thank you so much for that, Dr. Hong. Dr. Hong, Nidhi over here is asking us, how can students who are from non-computational backgrounds get started with things like atomistic simulations and these things?
Yes, that is one of challenge I faced before when I was a PhD student. This is kind of like very from zero background or scratch is non-straightforward to learn everything because in my about 10 years ago I did everything using all the Linux based OS and typed everything like coding. This is challenging, but these days after 10 years later there's like software company developed like GUI, graphic user interfaces software. We no longer have to write down all the coding like text-based thing. You can even use this software on Windows or Mac, and then you can just play with like GUI, just click the software and then run the software and then model the software using like all the screen, and then it's pretty straightforward for now. And also that software company that I'm using, that I'm collaborating, they are offering very well documented tutorials. So I'm sure I also have teaching material for that tutorial. So once they start, I'm sure within 4 weeks, 5 weeks, they can be like, I'm not saying that they can be like expert, they can be like intermediate level. So, so I'm sure they can learn very fast compared to the previous my year that I worked on the first time worked on MD.
Got it. Thank you so much for that, Dr. Hong. Dr. Hong, a question which has come up with Mumukshu is asking, do such RMD simulations have applications beyond material sciences? Do they have applications in biomedical or pharmaceutical research as well?
Yeah, sure. The MD simulation can be applied to any field in any STEM field. It's not limiting to engineering. You can do biochemistry, biomedical, and also chemistry or agriculture, where all the chemistry exists. So basically, we want to understand the chemical reaction at the atomistic level.
Got it. Thank you so much for that, Dr. Hong. Dr. Hong, one more additional question. With the
Yeah.
recent Make in India initiative, many of the students want to work on their own products with the aim towards making India a manufacturing hub. How can students get the exposure of working on such high-end materials and such simulations to build their own products before they join the program?
Okay, so for example, in US here, uh, maybe the best part is to collaborate with faculty instead of working alone. so they can reach out to faculty. For example, me, I have multiple projects working on the collaborating with industry. For example, designing as I introduced, designing higher performance of glass ceramics or like hydrocarbon fuels. So once they initiate the discussion with their faculty, they can set the discussion for, that's it, the choose the topics and then working with faculty to working on that topic for high performance engineering material. That's my suggestion.
Got it. Thank you so much for that, Dr. Hong. Dr. Hong, a couple of last questions. One of them, which has come from Sajal over here. She is asking, what are the biggest challenges in modeling nanostructured systems and how can we overcome those?
Yes, so my first suggestion is to comprehensive literature review before starting modeling. So if you do something from the zero background or scratch, even if you build something, that does not make sense in general. Do read paper from other researchers, what they have done or what they have not done. Once they have the first level, the knowledge on that, they can better design or they better model their structure for their MD simulation. This is, I always uh, talk to my student. Let's do the literature review first before moving forward. Then you can just do better outcome. That's my suggestion.
Got it. Uh, Dr. Hong Chaitanya, who has joined us, is asking how do RMD simulations work and if when compared to other simulation techniques, and how do they better perform in terms of accuracy and computational efficiency?
Right. So, okay, that's great question. So maybe you guys have multiple scale simulation. Do the very bigger scale. CFD, for example. CFD, the minimum element is like very like small, very small box or square. That's the minimum element for to simulate the phenomena in nature. In MD, we are simulating at atom. That's the scale, minimum scale in MD simulation. And for the smaller one, quantum mechanics DFT simulation, we are simulating motions of electron even. This is a very expensive one. CFT cheaper than DFT, and then MD is middle. However, MD is still expensive because we are simulating atoms, motions of atom. For example, let me give you the number. So for example, if I want to simulate MD simulation, my lab uses like 64 to 128 cores of CPU. In general rule, if I have 1,000 atom, we need one core. For example, if I do, for example, say 64,000 atoms, I need 64 core to simulate. That's its like computing resources that requiring. Okay. So anyway, this is the middle between the DFT and CFT. And in terms of accuracy, the MD is pretty accurate because this one is basically from DFT parameter, the optimization. So we always validate MD with DFT and also validate our result with the experiment or CFT. So overall, uh, once you have all validation, we can say, okay, this is fair, this is reasonable to report. So this is how RMD works.
Got it. Thank you so much for that, Dr. Hong. Dr. Hong, one last question. If you have time and if you may allow, then I'll
Oh
take this
no,
up.
go ahead. Yeah.
Sure. With the advent of generative AI, we are in the age of Gen AI right now. How do you think does it play a role when it comes to running simulations for testing out high performance materials, etc.?
Yeah, so the first of all, generative AI is a great tool for the beginner. For example, like I mentioned, there's GUI software and there's another software based on like text typing, coding. So generative AI will provide like initial input file. For example, you can just type like using ChatGPT, for example. I want to model something like aluminum metals, and I want to simulate something like I want to like do tensile simulation. And generative AI will create your input file based on your input, and then for now, I tried it before, but it's not perfect for now. But you have to validate the code before using it. But right now, it's not perfect, but I'm sure this will be developed in a very fast, in a year, few years. You can get perfect input file to simulate your structure or model using generative AI.
Got it. Thank you so much for that, Dr. Hong. Dr. Hong, it was wonderful to have you with us. Thank you so much for answering all the student queries and for your expertise on the topic at hand as well. Thank you so much for
No
spending
problem,
your
my
time.
pleasure.
Yeah, yeah. It was a pleasure to have you, Dr. Hong.
Thank you, thank you.
Yeah. All right. With this, before we move ahead with the next segment for our session today, I would be quickly launching another poll, and here it is on your screens. So, to everyone, all the 167 attendees we have on the call right now, if you can let us know what is your primary reason for attending this masterclass. Are you looking forward to professional development? Are you looking forward to getting more interest in research? Is it on the lines of academic curiosity or career exploration, networking, or any other reason which you may have? We would be waiting for another 8 seconds. Last 5 seconds. All right. So almost 90% of y'all want to know more about research interest, academic curiosity, or career exploration. Wow, that's wonderful. So with this, to explain a bit more and help us guide with the programs, eligibility, funding, scholarships, and each and everything which is there with Loyola Marymount University, Franca CEO School of Engineering, I now hand over the floor to Emily.
Hi, everyone. As Moen is introduced, my name is Emily Agnello. I am the Assistant Director of Graduate Recruitment here at Loyola Marymount University. And today I'm going to share with you a little bit about our university, our programs, admission requirements, scholarships, and how we support our students. So first off, where we are. So Loyola Marymount University is in the wonderful Los Angeles, California area. So as you can see from this map, that green kind of triangle is our campus. We are located on the west side of LA. We are ranked almost every year in the top 20 most beautiful college campuses in the United States because we have an absolutely stunning campus. Our campus does overlook the Pacific Ocean, as you can see. So we're right around the corner from Venice Beach. You can see the Hollywood sign actually from the side of our campus, and you can kind of see the Hollywood Hills. And now we are excited to say we are right down the street from where the 2028 Summer Olympics are being held. So a lot of really exciting things happening right by our campus. Also, close to our campus, we have an area called Silicon Beach, where a lot of large tech companies have headquarters. We're near Google, SpaceX, Boeing, Raytheon, all of the big science and engineering companies. And then we're also right next to, the film and television industry, being in LA, with all of Netflix, Paramount, Sony, all the big studios near us too. So a little bit about LMU. So we were founded in 1911, but we are based on about 500 years of Jesuit traditions. So we are a Jesuit institution. So our mission is very important to us. Our LMU mission is the encouragement of learning, the education of the whole person, and the service of faith and promotion of justice. Our mission is really shown throughout all areas of LMU, especially our curriculum. We really want our students to come to LMU and learn what they want to learn. So we do encourage you to make the most of your experience at LMU, gain the education and the experience that you are looking for, And then we also really hope and encourage all of our students to go back to their communities and make an impact. We really want you to make a difference for wherever you are living in the future with your LMU education you're receiving. So a little bit about 2 of our 7 colleges. So I'll touch on our Science and Engineering College and then our College of Business Administration. These are where our STEM designated programs are. So within our Seaver College of Science and Engineering, all of those programs are STEM designated. So we have civil engineering, which has environmental engineering and water resource engineering within it. We have computer engineering, computer science, electrical engineering, environmental science, mechanical engineering, and healthcare systems engineering. Any of these programs can actually be paired with our MBA as a dual degree. So you would graduate within 3 years with an MS in engineering and then also your MBA. And then within our College of Business Administration, we have an MBA program, accounting, taxation, business analytics, entrepreneurship, and management. Within our College of Business Administration, our accounting, taxation, and business analytics programs are our STEM designated programs. So LMU as a whole, we have a little over 10,000 students, so we're a medium-sized institution in the US. About 3,000 of those are graduate students. So those are including our students on our main campus and also from our Loyola Law School. And about 10% of our students are international students. So we do have students coming from all over to attend LMU. Something really important to us is our graduation outcomes and our career and professional development. So 99% of our graduate students are employed or pursuing further education after they leave LMU. So we have a very high placement rate for all of our graduating master's students once they leave LMU. The median salary they're earning is a little over $129,000 per year. And LMU has over 100,000 alumni. We have about 50,000 different employer partnerships. So we are really well known in the LA area. And our alumni really help connect our current students to different opportunities. So we really encourage our students to attend alumni mixers, alumni panels, and really connect with the students who were at LMU before them. We have an online platform called The Pride, which is kind of like an internal LinkedIn for LMU students to connect with our alumni. So you can search our alumni by the companies they work for and really be able to connect with them on a more personal level based off your interest. And then our career and professional development office offers career coaching, career fairs, fellowship workshops, help you connect with internships. So there's a lot of different ways to connect with and gain career and professional development opportunities while at LMU. As you can see, these are just some of our top employers. As I said, we are right around the corner from a lot of the big tech and aerospace companies in LA. So a little bit about application requirements. So every program is going to have some specific application requirements that aren't listed on this page. So I definitely recommend looking at the program you're interested in and seeing what their exact requirements are. We do require a bachelor's degree, a 3.0 GPA or higher, a resume, a personal statement stating why you're interested in coming to LMU, 1 to 2 letters of recommendation. These can be professional or academic. We require an official transcript and an official transcript evaluation from a US-based evaluation company. And then the language proficiency scores, we accept TOEFL, IELTS, and Duolingo. These can be waived if you reach out to our office, and we can connect you with the correct people to help you get that waived too. And then the application fee waiver for today is SEED. So when you're applying to LMU on the additional items, the additional information page, you'll put in the promo code SEED in order to get your application fee waived. A little bit about scholarship opportunities. So we do have graduate research and teaching assistantships available at LMU. Once you're admitted, you can reach out to your department and they'll typically help kind of connect you with different labs you might be interested in working in, or all of our graduate assistantships are posted on our student jobs page that you have access to once you're admitted. We do offer merit-based scholarships. So these are scholarships offered to you at the time of admission. So based off the strength of your application, you would qualify for one of the merit-based scholarships. We do also participate in the Seed Scholarship Fund. I know Moen put some information about that in the chat, so feel free to look at that. But we do offer multiple scholarships up to 50% of tuition through the Seed Scholarship Fund. And once again, there's an application fee waiver. Our application deadlines are all a little bit different. So we do have rolling admissions. So when you apply, you will typically receive an admission decision or in the College of Business Administration, at least an interview within 2 to 3 weeks of your application being complete. So definitely look at these deadlines when considering when to apply. I always encourage students to apply earlier than later, as the earlier you apply, the more opportunities there are for you typically financially, and also, assistantships are more available the earlier you apply too. If you have any questions after this session, please contact me. If you email the general graduate admission email, I typically respond to that too. So feel free to reach out to us. Myself or any of my colleagues will be able to assist you. Follow us on social media. We do post about upcoming information sessions and opportunities there within our office. I'm going to stop sharing my screen and answer any questions we might have.
Thank you so much for your presentation, Emily, and for being kind enough for answering many questions while they were coming through by the students throughout the session. Emily, couple of questions which are on the chat right now. Harshita is asking us if you can highlight few of the support services which are generally provided to international students by LMU.
Yeah, of course. So the first office you actually will all be working with is our Office of International Students and Scholars. So we call them OISS. They're the office that will help you apply for your I-20, receive the visa. They'll be the office who hosts your international student orientation. They'll help connect you with housing on campus and really be able to make that experience and transition to LMU a little bit easier. And then also throughout the year, they host different international student events. So they host like gatherings, get-togethers, events. So they're constantly bringing together our international students so that they can connect and get to know one another. And then we also have our office of fellowships. So we have an office that's specifically there to help you apply for fellowships, which is another way to kind of receive funding for your studies. So they're there to support you through that. Then our career and professional development office is also a huge help as they connect you with internships. They host a lot of professional development events such as resume workshops. They also always have at least twice a year a day of just like headshots for graduate students. So they'll bring in a professional photographer to be able to, spice up that headshot to make sure it's up to date for your resume and your LinkedIn. And then our College of Science and Engineering itself, they bring a lot of alumni speakers in. They have big speaker series throughout the year. So that's kind of the professional and academic side, but then also LMU has everything from an on-campus gym. We have intramural sports. We really do want you to kind of still enjoy yourself as a person when you're at LMU. It's not all academic all the time. And then we have a group called the Graduate Students of LMU, and they have graduate student get-togethers with students across all of our 7 colleges at least once a month. So I know they had a loft night the other night, and they all met up and hung out. They've gone to Topgolf. They've done all different kind of activities around the LA area. So there's different social and academic ways for you to be involved at LMU.
Thank you for that, Emily. Emily, a question has come up by Isha. She's asking, how does LMU support international students in terms of research collaborations and career opportunities?
Yeah, so for when it comes to research opportunities, the College of Science and Engineering would be your go-to. So once admitted, you can reach out to our Associate Director of Graduate Programs, and she will be able to kind of talk to you and see what your area of interest is and what your experience is, and then be able to connect you to the correct faculty members and labs. So we really do want your experience to be personalized based off of yourself, your experience, and your knowledge. So they're there to kind of guide you through that process.
Thank you for that, Emily. Emily, I know we are right on dot with the time. One last question is for all the students who are applying to LMU for fall 2025. What would be your final advice or any tips which you would like to give the students?
Yeah, so my final piece of advice is to do your research, find the program that you're interested in. There's so many programs out there. So really just trying to figure out what you really want to study in the future. And then also when you're applying, to be your authentic self. Give us the real reason why you're interested in going to grad school, why you think LMU is going to connect with your professional career goals. Really just be yourself as much as you can through that application process, so we can really see who you are as a person and see how you'll fit at LMU.
All right. Thank you so much for that, Emily. Thank you so much for answering all the student questions and guiding the students throughout the entire process. It was wonderful to have you and Dr. Hong with us. Yeah.
Thank you, Moen.
Yep. All right. One last announcement before we close the session. The final deadline for the scholarships offered by Loyola Marymount University Frank R. Seaver School of Engineering is 15th of March. There are 3 awards covering up to $25,000 of your tuition fee. The link to apply for the scholarship is put up in the chat. So for all the students who are looking forward to applying for fall 2025 for any of the MS programs, feel free to go ahead and apply for the scholarships as well. And we would be sharing all the details regarding the application fee waiver and rest of the details regarding all the programs offered by Loyola Marymount University as well post this session. So look forward to receiving that email from our end. Thank you so much, everyone. Bye-bye, Emily. Have a good day.